Thanks, everyone. And with that, I'd like to invite our speaker, Tom, to come up. Tom is a Senior Geotechnical Engineer with Terracon in Raleigh. He's a professional engineer and Board-Certified Geotechnical Engineer. Tom received a Bachelor's in Civil Engineering from University of Nebraska-Lincoln and a Master's degree in Geotechnical Engineering from UC Boulder. He has 35 years of experience managing and executing a wide variety of geotechnical engineering projects. In his presentation today, we'll discuss the geotechnical aspects of stormwater control measures, design, construction. So I'm going to just pull up the presentation here so those on Zoom can follow along. We'll be all set. That should be good.
Very good.
There.
Thanks for that. Appreciate it very much. Thank you all for inviting me today to speak at the Eastern Branch of ASCE. This branch has always been special to me. I served as its Secretary Treasurer, Section Branch Rep, which we used to have, Vice President, President, and President or past President between about 1996 and 2001. So it's been a while since I was an officer, but it was really neat to see the installation of the new officers today. As Pat mentioned, my presentation today will discuss geotechnical aspects of stormwater control measures, and I will include some real-world project examples towards the end. The two main purposes of stormwater control measures are to control the quantity and quality of stormwater. One goal is to limit post-development runoff to an acceptable amount. And if you feel as a geotech I'm preaching to the site civils, please forgive me. That's not my intent. This can be done by detention or retention of stormwater. The other goal is to treat the stormwater to remove or decrease total suspended solids, nutrients, and other potential contaminants such as fuel and oil from vehicles. In order for stormwater control measures to function as intended, it is important that in the long term, they stay in their design conditions. I'm channeling Bill Hunt from NC State. Wet stormwater control measures need to stay wet, and dry stormwater control measures need to stay dry. Otherwise, they won't control stormwater quantity and improve stormwater quality as intended. Geotechnical conditions and issues are critical in meeting these key performance objectives. I don't think that wet pond there on the left is going to stay wet. The North Carolina Stormwater Design Manual provides design, construction, and maintenance requirements for stormwater control measures. It includes methods and design criteria for stormwater control measures to treat or limit pollutants and other damaging effects of stormwater runoff. There are numerous types of stormwater control measures used for site development, and there is no one type that is best for every site. Different ones are better suited for different aspects of stormwater management, such as sediment removal, nutrient removal, peak runoff reduction, and volume control. Additionally, each site has unique features, such as slope, soils, groundwater, size, and development density. The site civil engineer typically selects and sizes the stormwater control measures for a project. In order to function properly, it's important that stormwater control measures meet their long-term objectives. As I said, wet stormwater control measures need to stay wet. Those two up top, and dry ones need to stay dry. Okay, primary versus secondary. Stormwater control measures are classified as primary or secondary based on their performance from research studies for the removal of total suspended solids. Primary stormwater control measures must also be able to treat the design storm, which is 1.5 inches in coastal counties and 1 inch in the rest of North Carolina, that first flush you sometimes hear about. When a site has numerous physical constraints and the regulatory requirements are stringent, it can be especially challenging to find an appropriate stormwater control measure. In this case, it may be necessary to modify the stormwater control measure design for the site characteristics, or to provide a combination of them that are suitable in series, such as that sketch shows, where there's an initial wet pond holding the water, or a wet basin holding the water, and then an infiltration after that, infiltration basin. The most commonly used stormwater control measure for site development is probably the wet pond. The depth of the main pool of a wet pond is typically about 5 to 10 feet. The main pool level needs to be maintained at the vegetated shelf for the plants to remove the nutrients, mainly nitrogen and phosphorus. Wet ponds need to stay wet in the long term to function properly, and groundwater helps keep them wet if it's high enough. For seasonal high water table conditions below the bottom of a pond, a liner may be needed to keep the water in the wet pond, depending on the infiltration rate of the underlying soil or rock. Stormwater wetlands are constructed systems that mimic the function of natural wetlands. They use physical, chemical, and biological processes to treat the stormwater. The depth of the permanent pool varies from about 1.5 to 3 feet, and there are shallow water zones where the plants are planted that are maybe 0 to 9 inches deep. The wetland plants remove the nutrients. Stormwater wetlands need to stay wet to function properly, just like natural wetlands. Groundwater levels help keep them wet if it is high enough. It's not a natural wetland where groundwater is discharging it to, but if we do have groundwater discharging into a stormwater wetland, it'll help keep them wet. For a seasonal high water table below the bottom of wetlands, a liner may be needed, once again, depending on the infiltration rate of the soils and the rock, or rock underneath them. An infiltration basin can be an open basin, trench, or a below-grade pipe system. It needs to be above the groundwater in order to stay dry in the long term. I guess if you can design a precast box, you might be able to put it below the water table, but you might want to design it for buoyancy. The seasonal high water table in general for infiltration systems should be at least 2 feet below the bottom of the system. And the infiltration rate of the in situ soil is needed to design the infiltration system. These systems work best when there are soils with high infiltration rates under them, such as sands with an infiltration rate greater than 1 inch per hour. Bioretention cell is a basin that's filled with specialized soil media and plants, which remove the nutrients and other pollutants from the stormwater. The soil media is a homogeneous mixture of sand, silt, and clay, and organic matter, sometimes pine bark, fines, and it needs to have a minimum infiltration rate of about 1 inch per hour. Bioretention cells require a minimum of 2-foot separation from the seasonal high water table in order to stay dry in the long term. Obviously, they're wet when the storm water goes through them, but in the long term, the intent is that they stay dry. Bioretention cells require under drains unless the infiltration rate of the underlying soils is more than 2 inches per hour. Permeable pavements, Permeable pavements capture stormwater through voids in the pavement surface and filter the water through an underlying aggregate course or reservoir. The reservoir typically allows the water to infiltrate into the soil subgrade, provided the soil is permeable enough. Permeable pavements require a 2-foot separation from the seasonal high water table to work. Permeable pavements are designed to dewater the storm volume to the bottom of the subgrade surface in 72 hours or less. So the infiltration rate of the underlying soils is needed in order to calculate the reservoir volume for that infiltration and for that drawdown time. They work best and are most economical in soils with high infiltration rates. That's why we don't see a lot of them in the Raleigh area. Such as sands with an infiltration rate greater than 1 inch per hour, maybe down in Southern Pines or Wilmington, for example. Lower infiltration rates require a thicker number 57 aggregate base layer. For example, the number 57 stone might be 6 inches for a permeable pavement in Wilmington, but in order to make that same pavement work in Raleigh, that stone may need to be 2 feet or more thick. That's why we don't see a lot of them, because that'll drive up the price here in the Piedmont. Sand filters. Sand filters can be open bottom basins or closed bottom boxes. They need to be above the water table to stay dry. The sand media in them filters the pollutants. Open bottom basins often rely on the infiltration of the underlying soils, but they don't have to. And these also require a 2-foot minimum separation from the seasonal high water table. Level spreader filter strip. Personally, don't see a lot of these. Maybe you all have designed some level spreaders to spread out that stormwater flow. See them occasionally, but a level spreader filter strip consists of a level spreader that's typically a cast in place concrete lip or a small little wall, and a filter strip that is graded and grassed that filters and infiltrates the stormwater. Maybe something you could use in a chain or a series of stormwater control measures, or for a very small runoff area. Swales remove pollutants from stormwater by biofiltration, settling, and infiltration. They need to be above the seasonal high water table to stay dry. Swales are designed to pass the 10-year storm and not erode due to the flow velocity. Probably not going to use these on a steep slope where you might need riprap to prevent erosion, for example. Dry pond. I love the oxymoron, dry pond. But anyway, that's what stormwater control measure calls, or manual calls it. The primary purpose of a dry pond is to attenuate and delay the stormwater runoff peaks. Dry ponds hold water immediately after a storm event and drain to be almost completely dry between the storm events. Dry ponds are typically secondary stormwater control measures. I showed you a picture before of wetlands. That's a site in Raleigh near Umstead Park where I used to walk my dog. This is the dry pond further downhill, probably the secondary SCM for that. Also would walk my dog near it. So I figured I'll go back there and take some pictures. Dry ponds can be used in a treatment train, like I talked about, such as a wetland or bioretention cell. They only require a modest separation from the seasonal high water table, maybe 6 inches. The idea is if they're wet somewhat, we're just trying to control the volume. They're not a main treatment stormwater control measure for quality. Kind of talked about the geologic settings, Wilmington versus Southern Pines, Pine Hills, Sand Hills. Geotech, we got to talk about geology here. North Carolina has 4 general geologic settings: west to east, Blue Ridge, Piedmont, Triassic basins there in green, and the coastal plain. And each setting has its predominant soil types, rock types, groundwater condition. And these factors, such as permeability of the soils and the depth of groundwater, really influence which types of stormwater control measures are more common in each setting. The table there is just sort of my stab from my experience working in all 3 geologic conditions. I've worked in Raleigh, Wilmington, and Charlotte over the years, and how based on soil, rock, groundwater conditions, you might see more stormwater control measures in one geology for another. For example, permeable pavements, probably more coastal plain. Biofiltration or infiltration systems, also more coastal plain, for example. Okay. There are multiple geotechnical issues that need to be addressed as part of the design of these stormwater control measures. These include seasonal high water table, infiltration rate, soil composition, earthen impoundments, and liners. Determining the elevation of the seasonal high water table is an important step in the hydrogeologic design process for stormwater control measures. The seasonal high water table is the highest level of the saturated zone in soil during a year with normal rainfall. It typically occurs in North Carolina between November and March due to lower evapotranspiration rates by plants, cooler temperatures, and wet weather with slow soaking rainfall. We get our peak rainfall maybe in the summer, July, August, hurricane season, September, but those storm events are large, brief, high runoff. The ones in the wintertime tend to be soakers, more infiltration. They tend to influence the seasonal high water table more. And the plants not being active with evapotranspiration in the wintertime does make a big difference. The seasonal high water table cannot be determined for permitting and design from published soil maps or geotechnical borings alone. It's not the same as groundwater levels measured in geotechnical borings. We get this all the time, but your water is this deep in the boring. Well, that might not be the seasonal high water table because that's just at that location on that date. If I drill in the middle of July versus January at the same spot, seasonal high water table could be quite different, or the water level at my boring logs could be quite different. And for example, this is a boring log from a site down near Hamlet where we set a piezometer, and even over a 2-week period in April of this year, we had a 2-foot variation. And that's in a 2-week period of April in the same year in one location. And based on some subsequent follow-up, we think that the seasonal high water table at that location is actually a few feet higher. Now, this is a preliminary study. This hasn't gone to design. We haven't had our soil scientist out there to verify that. But I just use this as an example of typical fluctuations in water table conditions. Okay. To function properly, wet stormwater control measures, such as wet ponds and stormwater wetlands, can utilize groundwater to help them maintain the long-term pool elevation. So if you have your seasonal high water table within that depth of your stormwater control structure, maybe that water table will help keep water in it, in addition to the storm flow that civil engineers are designing to get into these types of facilities. Most dry stormwater control measures are going to require the minimum of 2-foot separation from the bottom down to the seasonal high water table, and these include infiltration systems, permeable pavements, sand filters, and bioretention cells. The separation distance allows for short-term mounting of the groundwater in the unsaturated zone during infiltration down from the stormwater control measure without causing groundwater to flood the stormwater control measure. The manual also says that with detailed modeling, you can limit that distance to 1 foot if you can prove that it's not going to mound up into the stormwater control measure. I'm not a hydrogeologist who runs those models enough, but every time I've talked to them about doing it, it's like, yeah, give me $10,000, I'll run your model for you. And the civil engineers will come back and say, well, I'll raise it a foot. It's easier. The seasonal high water table depth should be determined by a licensed professional using redoxamorphic features, which are basically color patterns in the soil that indicate the presence of iron and manganese compounds that have been oxidized or reduced. Since this evaluation depends on soil horizons and soil morphology determined by soil scientists, we at Terracon recommend that a licensed soil scientist or someone working under their responsible charge determine the depth of the seasonal high water table. I'm a geotechnical engineer. I'm not going to go out to a site and do a hand auger and determine the depth of the seasonal high water table. I would rather send a licensed soil scientist or someone working. I wasn't trained as a geotechnical engineer on redoxamorphic soil colors and features. I do know what a Munsell color chart is, and that's about it. Thomas got to kick it out. The depth of the seasonal high water table can be determined using a hand auger, a soil boring with split spoons, or macro cores. We're doing a lot of that with our geoprobe push rigs with CPT. Cone penetration testing. Hand augers are commonly used in the Piedmont and the coastal plain. However, where there is hard, shallow soil or shallow weathered rock, or where their seasonal high water table is about more than 8 to 10 feet deep, we may need to do soil borings. Hand augers can only go so deep. And sometimes you get driller refusal rather than material refusal, but it's pretty hard to do a hand auger more than 10 feet deep. This is common in the Triassic Basin and parts of the Piedmont, where we'll send our soil scientist out with a drill rig to look at the soil samples that come up from the split spoon samples. Okay, perched versus apparent. A water table is perched if free water is restricted from moving downward in the soil by a low permeability layer. There is a dry or partially saturated layer of soil underneath that wet layer that's perched on a low permeability material. A water table is apparent if the free water is present in all the horizons from its upper boundary down through the subsurface profile. Keep in mind, perched conditions can be seasonal. Sometimes it's perched in the winter. You go out in the summer, you don't find perched water, same spot. An excavation in perched water table won't necessarily fill up with groundwater and stay wet, but one in the apparent water table probably will, like that example from the construction excavation in downtown Raleigh that I'm showing you there, which is under construction right now. Also, conditions which lead to seasonal perched water table conditions, such as infiltration, are often modified during construction by grading and new impervious surfaces. Wet stormwater control measures should not rely on perched groundwater to stay wet. And dry stormwater control measures won't necessarily become saturated on sites if the water table is predominantly perched. If we modify the site drainage, maybe we eliminate the perched water table condition. And this is a significant issue for sites primarily in the Triassic basins, Research Triangle Park, Durham, for example, West Cary, where the permanent superficial aquifer groundwater is typically much deeper than that shallow perched water table. Well records in Triassic Basin will typically show you a ground aquifer type apparent groundwater, really no shallower than 10 to 40 feet. And it's usually down in the fractured weathered rock. So if you get a seasonal high water table report that says, oh, I'm in the Triassic Basin in Durham and the seasonal high water table is at 2 feet, you can dig a hole 15 feet deep and it might never fill up with water. So you need to keep that in mind. And sometimes it doesn't hurt to ask, you know, is this perched or apparent? Okay, infiltration rate. Determining the infiltration rate of the in situ soil is also an important step in the hydrogeologic design process for stormwater control measures. For infiltration devices and permeable pavement, infiltration of water down through the in situ soils is necessary for treatment and volume control. The infiltration rate is needed to design those stormwater control measures. It's also advantageous and sometimes necessary to have low permeability in situ soil for systems with permanent ponded water like wetlands and wet ponds. Infiltration rates should also be determined by a licensed professional, such as a soil scientist, geologist, or engineer. Us engineers, we can run a double ring infiltrometer. We don't have to get a soil scientist to do that. So, but that's fine. We got soil scientists out there. Maybe they can do both. The test methods include the double ring infiltrometer, and what you see pictured at the bottom there is a constant head permeameter. And since we're in Raleigh and we have a lot of state grads, we still call it the Amuse-meter after Dr. Amuse. Any of you may be familiar with Dr. Amuse, who kind of came up with this thing, I think in the 80s or early 90s. I don't know. We've been using it for a while. I've never run one, so don't ask me how to run one. The North Carolina Stormwater Design Manual discusses test pits and double ring infiltrometer testing to determine the infiltration rates, and it provides recommended test frequencies for infiltration systems. Not necessarily for your other systems, but it does for infiltration systems. And it also states that constant head permeability tests with a constant head permeability or permeameter are acceptable alternative to a double ring. You don't have to run double rings. Those can be expensive and take a little more time. Earthen impoundments are used to obtain water storage volume for water treatment and or water quantity control. They can be constructed by excavating existing soil and rock down below the surrounding grades, and they often include fill materials as embankments around part or all of the stormwater control measure. These embankments function as dams, which should be designed in accordance with the North Carolina dam safety regulations. And water detention basins may be regulated as dams by DEQ if they have a high hazard potential, are higher than 15 feet, or impound more than 10 acre feet of water. Personally, I don't see a lot of stormwater ponds that get that big on most sites, but maybe if you had a huge residential or commercial site with all the water going to one big pond, you could end up with a dam that needs to be regulated by dam safety. But from a geotechnical standpoint, whether the dam is high hazard or 8 feet high or 6 feet high, it's always a good idea as a geotechnical engineer to be thinking about and possibly evaluating settlement, slope stability, and seepage. Okay, slopes. Slopes for earthen impoundments for stormwater control measures are generally no steeper than 3 to 1. Certainly those above the water table to maintain that grass cover and for equipment maintenance equipment. The geotechnical engineer should perform slope stability analysis for slopes steeper than 3 to 1, including the interior side slopes of wet ponds due to potential rapid drawdown conditions. Still see a lot of wet ponds. Hey, the site's tight. I got to use 2 to 1s on my interior side slopes. Is that okay? Well, sure. As a geotechnical engineer, let me check it out and make sure it's okay. Maybe for a site in Wilmington in sands below the water table, it's not okay. Maybe for a site in Durham with the good silts and clays, it's perfectly okay. Seepage must be considered in the design of these embankments for stormwater control measures. Seepage can cause internal erosion or piping within these earthen embankments, which can lead to embankment failures like that picture I showed early on. It can also cause slope instability due to reduced effective stress, reduced effective shear strength due to the pore water pressures. For some stormwater control measures, only the short-term seepage really needs to be considered, but for most of them, we still look at long-term seepage because the permanent pool is above that toe of embankment elevation for most that I see and we deal with. So as long as you have a permanent pool elevation higher than the toe of your embankment, you have a potential for seepage through that embankment. Seepage forces can be reduced and controlled to safe levels by using a low permeable, as one noted on the sketch there, a low permeability material such as silt and clay for the embankment, low permeability cutoff trenches below the embankment, concrete pipe cradles, or anti-seep collars or seepage diaphragms along the outfall pipe. If the embankment material is not low permeability soil, then an impervious core can be included in the design as shown in this example. For stormwater control measures, low permeability soils typically include silts and clays, but they can also include clay sands with at least, I would say, about 30% fines, maybe 20% fines. Sometimes we see these specified, oh, it's got to be a silt and a clay. Well, these aren't the same as a landfill liner, or we're not trying to protect the environment from contamination. We're just trying to keep the wet pond wet or the wetland wet. We're trying to keep water in them. So there are some other soils, clay sand, sometimes silty sands will work. And we're generally looking for about, well, the North Carolina Design Manual, the liner requirements say 1 times 10 to the minus 5 centimeters per second, or about 0.01 inch per hour. So if we can have that same material in our embankment, we know it's going to effectively act as a liner and not let water seep through it too fast. And of course, if necessary, but rarely done, the geotechnical engineer can perform a seepage analysis to determine if an impervious core or a cutoff trench is necessary. Sometimes I just see designers, we're just going to use a cutoff trench and not worry about it. That's fine as long as you have suitable soils on site and you don't have to blast rock to build your cutoff trench. Liners. When the bottom of a wet stormwater control measure, such as a wet pond or stormwater wetland, is located above the seasonal high water table, and the underlying soils and rock are too permeable, a liner may be needed to sustain that permanent pool. A liner may be needed if those underlying soils have high permeability as well, even if the seasonal high water table is within that basin. If you have your seasonal high water table within the basin, but it's still going to infiltrate out, you may need to consider installing a liner under your wet pond or stormwater wetland. Typically, if the in-situ soils have a permeability greater than that 0.01 inch per hour, you want to look at installing a liner in your stormwater control measure. The other thing that we get into a lot in the Triassic Basin, Durham, Research Triangle Park, is fractured, partially weathered rock. We'll see a wet pond excavated down 10, 15 feet, and it's nothing but fractured weathered rock, which maybe the contractor can rip or has to blast. And we get asked all the time, will my pond hold water? And you're like, well, if the rock is too fractured and the water is another 20 feet down, maybe it won't. But there are things that we can do. If you want to be conservative during your design and hedge your bets and make sure the contractor's got it in their bid, put a liner in your design. If you want to roll the dice during construction and determine if the pond will or won't hold water, that's fine. But if the contractor needs to install a liner, we all know the contractor is probably going to justifiably ask for a change order. Liner options include soil liners, geomembranes or polymer liners, and bentonite liners. If a soil liner is selected, I recommend laboratory testing of on-site or potential borrow soils be done up front to identify a suitable liner material, including classification, compaction, remolded permeability. The geotechnical engineer can certainly assist the design civil engineer with developing soil liner specifications, or I've helped them with geomembrane liner specifications before. Some of the civils may not be familiar with geomembranes in these applications. So happy to help if we need to as geotechnical engineers. And there are multiple, also, we've been talking about design, but during construction, there's multiple geotechnical issues that need to be addressed as well. And these are going to include sedimentation basins, which are converted to stormwater control measures, the bottom infiltration rate, soil media composition, embankments, liners, and certification. Temporary sedimentation basins are often used for erosion control during construction, and they're often converted to permanent stormwater control measures such as wet ponds or stormwater wetlands near the end of construction. The construction of temporary sedimentation basins should be observed and tested during the initial construction before they fill with water or sediment. It's really difficult to perform adequate compliance testing at the end of construction if the embankment and the outfall pipe were installed months before during the initial construction. I've had projects before where they've called us up and said, well, we built our pond, come certified. I'm like, when did you build the pond? Well, 9 months ago when it was a sedimentation basin. We weren't out there testing and observing at that time. How can you expect us to certify its compliance with your plans and specifications? For many types of stormwater control measures, the bottom infiltration rate should be tested during rough grading. For example, wet ponds above the seasonal high water table designed without a liner, we need to verify that the in-situ soils will retain that water in the SCM at the bottom of it. The boring logs might indicate that they should, but we still need to verify that during construction. And for your infiltration devices, such as your permeable pavements and your infiltration basins, we need to verify that the minimum design rates are met, that the water will infiltrate fast enough. Soil media, which is used in the stormwater control measures to biofiltrate pollutants and provide nutrients for the plant growth and allow for storage and slow release of these stormwater flows. The important properties of the media include soil texture, structure, organic matter content, and the microorganisms within them. In some stormwater control measures, such as bioretention cells and sand filters, hyperpermeability media is required. Once a contractor identifies the media source, testing of the sample should be performed to confirm it meets the project requirements for gradation and permeability. Pre-mixed bioretention cell media is available from some landscaping material suppliers. And I basically just asked them to give me a submittal with some lab test results, and then we don't have to repeat those lab test results necessarily. If it's a pre-mixed media or maybe a masonry sand from a local quarry. I'm not saying we have to test the heck out of it, but if we can be sure that we're getting what we are designing for, it's always a good idea to confirm that during construction. Embankment materials need to be tested for classification, make sure they're low permeability enough soil, and compaction is important, like on every earthwork job that we do. Outfall pipe installation, including any cradles, anti-seep collars, seepage diaphragms, need to be observed. Photograph, please. If concrete anti-seep collars or cradles are used, we often will do concrete compressive strength testing just to make sure that the material supplied. Sometimes we do. Not that big a deal. It's not a heavy structure. But I've been asked to do compressive strength testing on concrete cutoff walls or cutoff collars before. Liner installation may require dewatering efforts to provide a relatively dry, stable subgrade for the liner, especially for excavations with groundwater seepage. Maybe we're excavating this pond in the wet winter with perched water table conditions in Durham, and for 2 weeks the water seeps in it. Well, the contractor needs to be prepared to handle that. Normally, you're not going to be building so far below the apparent water table that dewatering for these is a big issue. If bentonite is mixed with the soil, we recommend maybe some laboratory permeability mix designs prior to construction. Bentonite's not cheap. How much does it take? Can't answer that question until I mix some bentonite with your soil and test it. The construction materials testing firm should observe and document the installation of any geomembrane or polymer liners, and oftentimes the installers will supply quality control for their welds and joints, which is fine for stormwater ponds, in my opinion. In general, for certification, it happens, but we're asked to certify, if you will, the construction of these. And that's going to take that the materials testing firm coordinate with the project team to observe and test them for compliance with the project civil drawings. For example, the city of Durham does require a certification form prepared by the geotechnical engineer with testing reports, photos, materials submittal, and the geotechnical engineer's resume attached. It's not a good idea to wait till the end of construction to ask the geotechnical engineer for a certification if the geotechnical engineer was not involved with the project during construction. Kind of hard to certify it if you or the people that you work with weren't out there checking all the boxes and doing everything they needed to do. And I've been asked to and refused to a couple times certify ponds or embankments in Durham because the data just wasn't sufficient. But then we normally have to go back and do additional testing and try to see if it works anyway. I think I've got time. Doing okay on time? Yeah. I'll discuss some project examples, some real world project examples, which are intended to demonstrate some of these issues that I've been discussing today. The Hillsborough Park and Ride project consists of a new public roadway with bus traffic and a personal vehicle parking lot. Terracon initially drilled borings for the proposed grading and pavements, which encountered some clay fill over Piedmont residual clays and silts. Groundwater was not encountered within 10 feet of the ground surface. The site civil engineer then let us know that they were considering using a stormwater treatment swale on the south side of the parking lot, which was going to be excavated only about a foot below the existing grade. Smaller project, small runoff, treatment swale, probably one of the only treatment swales that I've been involved with. So then the site civil engineer requested some input for the design of that treatment swale, including an infiltration test. Terracon, we don't locally have licensed soil scientists in-house. There's some good ones that we work with in the region. We subcontracted one of those, and they evaluated the depth of the seasonal high water table and tested the infiltration rate as requested. They used a borehole permeameter and a hand auger boring to do that, since it was basically only going to be excavated down about a foot, and we needed to only go 2 more feet to make sure seasonal high water table was deep enough. And the results were very favorable for the treatment swale. The seasonal high water table is more than 90 inches deep. This is Hillsborough, Piedmont. Seasonal high water table, typically not shallow unless you're down near a river, creek, so that wasn't a problem. The infiltration rate was more than 1 inch per hour. A little bit surprising to me, I'll be honest with you. But I think some of the near surface soils in that area have been disturbed by past maybe construction, agriculture activity. It wasn't typically that real tight Piedmont red clay, and it infiltrated adequately. So we said, yeah, here's your data. And the civil engineer went for it and designed a swale. Hasn't been constructed yet, but as soon as it's constructed, we're going to be checking on it annually to make sure it's functioning properly, or at least I'll be driving by checking on it. This WNC3 project, it's a distribution center with a wet pond for stormwater management. It's located just outside of Tarboro, down in the coastal plain. The soil maps indicated a seasonal high water table at depths of about 6 to 48 inches at the site. And this is why I'm saying don't just rely on the soil maps. They're an indicator, but they're not accurate enough, in my opinion, for design and permitting. Our soil science consultant went out there and determined that the seasonal high water table at those 3 blue dot locations within the stormwater wet pond was 24 to 32 inches deep. The geotechnical hand auger boring that we did as part of the geotechnical evaluation, we got to 5 feet in September of this year, September 17th, and didn't hit water. So that's where the soil scientist says, hey, the soils are telling me the seasonal high water table is what, about 3 to 4, well, about 2 to 2.5 feet deep. And you do a hole and it's dry to 5 feet. Well, that doesn't mean I did the hand auger boring during a seasonal high water table condition. So that soil science is really, really needed in order to verify and determine that seasonal high water table. All right, so based on it's a flat site. The pond out there is going to be constructed by excavating below the existing ground surface. There's not an embankment on this thing. They're basically just digging a hole in order to build this stormwater pond. The seasonal high water table, it happens to work out. They were able to make the stormwater flow work out, and the seasonal high water table is about at that vegetated shelf layer, permanent pool level. For those of you designing these before 2017, the old regs used to say seasonal high water table shall be within 6 inches of the permanent pool. That went away in 2017, and that was hard to achieve. There's a variety of reasons. The seasonal high water table does not have to be within 6 inches of your permanent pool, but boy, if it is, you got a lot less to worry about. That wet pond will stay wet, at least under seasonal high water table conditions. The outfall pipe, the civil engineer went ahead and did design some anti-seep collars. And you're like, wow, that thing's really flat. There's about a 2-foot head difference between the permanent pool and the outfall pipe elevation. They didn't ask us to run a seepage analysis of those existing soils. Well, they're not existing soils because to install the pipe, they're going to have to trench it. The main thing about outfall pipes and seepage, and I don't think I mentioned it, it's really hard to compact backfill around pipes. So if you have a perfectly flat trench and you set a pipe on it, oh, I got a compact backfill underneath that low permeability clay, you can never get good enough compaction around that. So seepage collars or diaphragms, if you prefer to collect rather than dam up the groundwater, is something that I would always recommend for an outfall pipe. But another war story here, most of the outfall pipes that I've seen problems with do have relatively steep slopes and steep gradients. The ones that have blown out, saw one in Charlotte years ago, and it was like, wow, can't believe they put that thing in. So I don't think they're going to have any seepage problems on this site, but a couple seepage collars aren't that big a deal. Sorry. The other reason that we evaluated the soils, I mean, we're below the seasonal high water table. We wanted to make sure that the soils coming out of that pond, like every site, if we're going to do an excavation, can we reuse those soils for fill? And the answer on this one was, of course, yes, but you're going to have to dry them out, which is pretty much the answer you're going to get on any coastal plain site. You dig below the water table, the soils may be suitable for use, but they may be really wet and difficult to use. Talked a little bit about Durham School of the Arts. This project is going to include 4 stormwater wetlands for stormwater management. Terracon performed soil science hand auger borings to evaluate the seasonal high water table in addition to the geotechnical borings. I sent the soil scientist out there. And for this particular stormwater control measure shown here, the seasonal high water table was determined to be perched at 34 inches. Not surprising. The geotechnical boring did not encounter groundwater within 20 feet of the surface, and the design bottom of the wetland is 9 feet below the original ground surface. So if I have perched water table about 3 feet deep, and I'm digging 9 feet down to build my wetland, but I know water in my boring is 20 feet deep, and geologically I know the apparent water table is deep enough, and the soils might be a little bit silty and sandy, as shown on the boring log, silt, maybe some weathered rock. Do I need a liner? Well, I was not asked to answer that question. The civil engineer just said, we're going to put a liner under this thing. And they went ahead and put it in their designs. Now, does that have to be imported soil from offsite? No, there's plenty of silts and clays on this site. It's in Durham. All the contractor has to do is be prepared to save 6 to 8 inches of the clay and spread it out on the bottom of this thing and roll it once or twice, and they should be good. So sometimes people freak out. Oh, I'm going to need a liner. That's going to cost me $50,000. Well, not necessarily. If you got the on-site soils. The other war story I'm going to say, I don't know how many projects, contractor starts digging and they haul off the worst silts and clays. Oh, it's fat clay. I can't use that anywhere. It's unsuitable. And then it's time to build a liner for their pond because it won't hold water. What they hauled off 6 months ago would have been ideal material used for the liner. So sometimes, you know, you got to think holistically. Maybe the bad soil in one application underneath your building might make a good liner or a berm for your stormwater pond. But don't build a stormwater pond embankment out of strippings. I've seen a couple of those and they failed. All right, Durham School of the Arts, it's currently under construction. We're not using strippings. We're saving the material. The contractor is currently installing the temporary sedimentation basins, and we've been proactive enough with the project team to make sure that we're out there monitoring that work. And because we know at the end of this, it's in the city of Durham, we're going to have to do one of those city of Durham certification forms. But whether you're doing a certification form or not, oftentimes as material testing firms, geotechnical firms, site civil engineers, we're asked at the end of construction, hey, let's certify or confirm it was in compliance with plans and specs. You got to be out there when it's being constructed, not after the fact to do that. Murray Massenburg Elementary School, another project in Durham, also in the Triassic Basin. The soil survey indicated a perched seasonal high water table at about 3 feet to greater than 6 feet in one location. The geotechnical borings, once again, did not encounter groundwater within 10 to 30 feet of the surface. But they're only good at the time they were drilled, I get that. But 3 sand filters were designed to collect, detain, and treat the stormwater. I'm like, sand filters, okay. Well, you're not going to get much infiltration under them, but they don't need that. The sand filter media consists of 3 feet of that ASTM C33 sand, basically fine aggregate concrete sand. And, you know, they just got a grain size cert from the quarry, said this is what we're bringing. And we said, okay, that was fine. The grading plan and the material looked fine when we saw it on the site. The grading plan showed about 3 to 10 feet of cut, though, to get to the bottom of the sand filters, and it did have an earthen embankment about 9 feet high on one side of it. During construction, Terracon tested the embankment materials and the compaction. We observed the installation of the inlet structure and the outfall pipe. That bottom left photo shows you what I mean by setting a pipe on a flat subgrade. How are we going to compact around that? Well, you're not. We also reviewed the purchase receipt for the pipe, which Durham requires, and that's a fun one too. I can't certify this until the contractor gets me his purchase receipt for a pipe to make sure it's class 4 or better RCP. And we did provide certification for the dam and seepage controls. Not to throw anybody under the bus, this was in Durham. I don't know why there wasn't a concrete cradle under the outfall pipe. Wasn't on the plans and specs. They got approved. I didn't have to certify a cradle. So that, to me, that's between the designer and the city of Durham. If the Durham accepted it without a concrete cradle, that's fine. I'm not saying one was required. They did have seepage collars, so, and it's a pretty flat pipe. And the last project I was going to talk about today, to save time for questions, Milner Commons. This is a multifamily residential development in Raleigh, which includes a wet pond. The design bottom of the pond corresponded to residual silty sands, and it was above the seasonal high water table. So we got a wet pond above the seasonal high water table. The geotech boring says we got silty sands. Not the most low permeability material in the world, but nobody did any infiltration testing during the design phase. We didn't do geotech. Who knows why this stuff doesn't always get done. And the pond design did not include a liner. They thought, oh, we're going to be in, you know, good red dirt in the Piedmont, it'll hold water. Good red dirt is not a technical term. Sorry. So they use it as a sedimentation basin. They didn't have anybody test it, but then it was time to sort of, you know, basically make sure it works. We said, we can test it if you pump the water out. They pumped the water out. We did our, what water was in it. We did our testing, and the infiltration rate was 0.7 inches per hour. Well, that's about 10 times, almost 100, well, almost 100 times, but 10 times faster than that liner rate and the specified rate on the drawings of 0.01 inch per hour. So we concluded, hey, this pond may not hold water. What are we going to do about it? And then, well, let's evaluate it. So we did obtain some soil samples from the bottom of the liner or bottom of the pond, sorry. And yeah, we've got variable material. We've got fat clay with sand, elastic silt, and sandy fat clay and clay sand. looking at those samples going, well, maybe if we just roll this material and try to recompact it, we can get the permeability. Contractor said, I don't have time. I'm going to use bentonite. How much bentonite do I need? So we did a quick bentonite mix design, and they placed some bentonite, mixed it in with the on-site, or they actually imported some other soils because they didn't want to mess with what was on the bottom of it, and mixed some bentonite in it. And we ran an infiltration test again, and it was less than 0.01 inch per hour. So we all concluded, yeah, this pond will hold water like it's supposed to. We talked about a geomembrane liner because it would have been probably, no worries, don't have to mess with bentonite. And I don't know if this is true or not, but the project team told us, well, if we switch from a no liner / soil liner option to a geomembrane liner, we're going to have to re-permit it with City of Raleigh, I guess, and we don't have time for that. I don't know if that may be true. So sometimes the lesson I learned from that was, to me, the quickest and most technically feasible solution was, let's just put a geomembrane liner down and get one out there without, talking to the contractor about cost and schedule. But the answer from the project team was, no, we don't have time to take this thing back and get it re-permitted. We got to get this built, because they needed their CO last week, kind of thing, which I think they have now. Okay, so to summarize my presentation, the geotechnical aspects, certain geotechnical aspects, they do need to be addressed during the design phase of these stormwater control measures, including seasonal high water table, infiltration rates, embankments, and liners. And geotechnical aspects that are observed and tested and evaluated during construction include sedimentation basins converted to stormwater control measures, bottom infiltration rates, soil media composition, embankments, and liners. Also, as I've been discussing, certification for compliance with project drawings and specifications may be required for some projects. So with that, I'd like to thank you. And if I have time, open it up for questions. Pat, we got time? Okay. And to be prepared, I set an alarm for 12:55, so because as Henry and David know, I tend to get verbose. Do we have any questions?
Question.
Yes, sir.
And I'm not familiar with any of this stuff, so this is pretty elementary. I apologize.
No worries.
But it seems like a lot of your effort is to keep wet ponds wet.
Yep.
But I've seen a lot of dry, what I think are dry ponds, like they're dry all the time.
Yeah.
Is that okay? Or is that just a totally different kind of approach to stormwater? Right.
Well, a dry pond is a stormwater control measure that can be used, but they're mainly used for that retention to handle the peak flows, to keep that post-development flow less than or equal to the pre-development flow. But a dry pond, you don't get a lot of credit for nutrient reduction with a dry pond.
So that's the trade-off.
That's the trade-off. And I didn't even get into credits and nutrient reductions and all that. All these, which as a geotechnical engineer, we don't normally deal with that. But my general understanding is that goes into the selection of the stormwater control measures. There are certain areas where nutrient removal may be just or more important than handling your peak flows. Falls Lake watershed. Correct me if Henry, I remember all the fish kills in the Neuse River Basin in the 90s when we were here in Raleigh, and nobody worried about nitrogen or phosphorus coming off the parking lot until all those fish were dying down in the Tarpamaco and Neuse River. And then we all adopted the Chesapeake Bay rules down here in North Carolina, and we started saying, we need to handle, we've been handling stormwater quantity for years as civil engineers, but the quality aspect of it. And I think that's where certain SCMs you get more credit. And if you don't need the credit, maybe a dry pond will work just fine.
Okay.
Yeah. Does that make sense?
Yeah.
Okay.
Yeah, we got a question too.
Oh,
Go ahead first.
Small question.
thanks, Thomas.
On the multifamily project, so you took the infiltration rate as the average of the inner and outer rates?
Is that what it showed? Did we make a mistake?
It seemed odd to me. No.
Yes.
Is that typical? I thought it typically the inner, just the inner.
That might be a good catch. I need to go back and look at that. Man, I hate to tell them if we failed it and then we made them put a liner in there. See, that's where that quality. I found out about this project after the fact. Not that I would have caught that because I'm not a double ring pro, but if that's a point, I'm gonna go check on that right now. Because if that's a point, we need to correct that. you're right,
Yeah,
though. The
you
less-
see the flow, you just make sure it's flowing.
Yeah. 0 inches per hour, we should have passed it. And that's what was surprising. Okay. Thank you. Yeah, and I'm not here to sell Terracon or anything like that. I appreciate that. I really, really do, because that's what, professional societies and professionalism is all about. And maybe a peer review of that report wouldn't have been a bad idea. Thank you.
All right, so 2 questions from Zoom.
Yes.
One question is if Tom is performing any efforts in the North Carolina mountains after Hurricane Helene.
No, I have not been. I know that I was contacted about someone who had a slope failure right next to their mother's house, but we weren't supposed to go up there and look at it. So I referred them to some folks some geotechnical engineers in Asheville that might be able to help them out if they weren't impacted.
Sure. All right, second question is, what is a method of measurement for acceptable ppm of sediment at the final point of discharge?
Oh, as a geotechnical engineer, I can't answer that question. That's more of a stormwater design site civil issue, I would think. And I mean, I would certainly have to look that up. Occasionally over the years, we've been asked to check turbidity and sediment. But that's one of those things where here's your data and I'd have to find a site civil engineer who's more familiar with that than I.
That's it.
Okay. Anything else? Well, once again, thank you.